questions? Anybody have any homework questions?
I do have a homework question.
Yeah.
But just about a small part.
Okay.
You don't have to do the whole thing.
Okay.
It's for 3D.
Do you have it with you? I didn't bring the problems with me.
Yeah, multiplying by -3 and also subtracting. Okay.
So this is on vectors number 3. I'll go somewhere in between doing the whole thing and just so this is vectors.
An actual question is like 2 pages back from that.
Okay. So we have 2 vectors. This one has a length of 4.5, and it makes an angle of 20 degrees with the horizontal. And this is vector, this is the one we're calling A. And then B has a length of 3.8, and it makes an angle of 15 degrees with the vertical. And for part D, it says this is the coordinate system, x-axis up, y-axis to the left. And we want to calculate the components of 2a minus 3b. So the way to do that is we're going to calculate the components of each of these vectors, a and b, in this coordinate system. Okay, so this is 20 degrees. This is 15 degrees. So the vector A to go counterclockwise from the x-axis to the vector would be 270 plus 20. So you could use 290 or negative 70. So this is 4.5 times cosine and sine of negative 70. And then B is 3.8 times, so that angle would be, you'd go 180 and then another 15, so 3.8 times cosine and sine of 295. So it appears that yeah, 195, sorry.
I have the components of it.
Okay.
It's 1.54 and negative 4.23.
Okay. And then I think B, tell me if this is, oh. No, I don't have it here.
First component is negative 3.67.
Okay.
Is negative 0.98.
Okay. And after you calculate those, the if you're just plugging this stuff into your calculator, the easiest thing to go wrong is that you're in radians instead of degrees. You can usually catch that by just checking the signs. This is the fourth quadrant, so we should have positive x, negative y, and that's what we got. This one is third quadrant, so they should both be negative, so that one works. And now that we have those, we're just going to go 2 times 1.54 negative 4.23 minus 3 times negative 3.67 negative 0.98. The specific question you asked was about like the order of when do you use the negative or whatever. It doesn't matter. It follows the same rules as multiplying numbers, so the order doesn't matter.
For me, with the negative 3b,
Mhm.
I drew it going opposite way because it was negative 3.
Okay, that'll work fine, and then just multiply by positive 3.
Okay, and the answer will still be the same?
Yeah, it'll be the same. Yep. Just like if you have, just like if you're taking 4 minus 2, you can think of it as a negative 2 and you're adding it, or you can think about it as subtracting a positive 2. Vectors work the same way. Any other homework questions? Yeah. Okay. So last time we started talking about kinematic vector quantities. So we defined the position vector and we call it the same thing, lowercase p, but it has the symbol over the top, the arrow over the top to tell us that it's a vector variable. So now we have to define the velocity vector. And just like in one-dimensional motion, the velocity vector as a function of time is equal to the time derivative of the position vector as a function of time. And the way derivatives work with vectors is you just take the time derivative of the x component and the time derivative of the y component, and those are the components of the vector. Now so the way to think about the position vector is, I said last time, is just basically to think about the coordinates of the position vector is just the coordinates of the object in whatever your coordinate system is. The way to think about the velocity vector is like this. Every vector has two pieces of information, two properties, the magnitude and the direction. The magnitude of the velocity vector, and you denote that with the absolute value of the velocity vector, is the object's speed. Dramatic. So if you think of the surface of think of the surface of Minneapolis as like a plane. As you're driving around, and if you chose a coordinate system on the ground, you could measure your velocity as a vector wherever you're going. And if you took the square root of the sum of the squares of your velocity components, that would give you the magnitude, and the magnitude would be what your speedometer says. Okay. And the other property a vector has is the direction. And that's the direction the object is moving at that instant. So if you have an object moving along, so let's say this is the path that an object is following, and let's say it's going this way. Okay. And let's say this is the object at the time we're interested in. The velocity vector is always tangent to the path. Okay. And I want to try to be clear about something now. Notice that we've already, so now with this idea that the velocity is tangent to the path, we already have a way to draw two representations of motion. So there are two representations of motion that can look the same, but they mean very different things. The first one of those is a position versus time graph for a one-dimensional motion. Okay, so if you are dealing with one-dimensional motion and you have a position versus time graph that looks like, let's say that, and the place you're interested in is right here. Okay. Then the velocity is a number given by the slope. Yeesh. Okay, but now just to make this point, I'm going to use this same thing I just drew. Okay, so where's my, okay, so the second one, 2, is the path of an object in 2D. Okay. So in the case that you're dealing with motion along a line or one-dimensional motion, this is a position versus time graph, and this entirely lives in math world. Okay, it's a graph. Okay, it's not showing anything about what the object actually does. The object's just going back and forth along the line. This, that looks exactly the same as that, lives in the actual world, and it's like taking snapshots really quickly, following the motion of the object as it moves through space. I can't really do that. But so this is the real world, this is math world, but they can look the same. So when you see a picture like this, don't just be like, I know I draw tangents and whatever. You got to know what you're looking at, okay? So this is the physical world. This is math world. And in this case, the velocity vector looks like that. The velocity is a vector and that vector is tangent to the path. Any questions about that? Okay, so for an example, let's say that the position vector as a function of time is, well, let me do one that I can draw. So let's say the position vector is t and then t squared. So first, what's the velocity vector as a function of time? Second, what's the velocity vector at time, let's do 2 seconds. And then let's sketch the path. Let's sketch the motion in the physical world. So first, the velocity vector as a function of time is just going to be, take the derivatives of the two components. So this is going to be 1, 2t. And so now this is a function that'll give you the velocity vector at any instant. So at time equals 2, the velocity is 1, 4. And now, if this is our coordinate system, okay, so this is x and y, but this represents what's happening in the physical world, okay? The graph looks like this. So let's say This is 1. This is 2. So here's the path. And at 2 seconds, the object is at this location here. And the velocity vector is tangent to the path at that instant. So that's the velocity vector at time equals 2. Yep.
So that's a graph of the position equation?
This is just like if you like that thing where you take all the snapshots of the object's location as time goes by, and it shows it in space. It shows where the object's moving as it moves through its path, whatever the path is. Okay, so it's different than a position versus time graph. It just shows the path at every instant. Okay, you could do position versus time graphs in 2D, but people don't usually do it a lot because you'd either have to do a 3-dimensional graph, which is really hard to do on paper, or you have to do separate graphs of the X position and the Y position versus time, which is just sort of tedious to work with. Okay, so for the most part, any graphs of position versus time that you see are going to be for 1-dimensional motion. Okay, and the velocity vector, when I break it up into components, I'm going to call the components Vx and Vy. Okay. And then the last thing we have to define is the acceleration vector. The definition of the acceleration vector as a function of time is the time derivative of the velocity vector as a function of time. Which is the second time derivative of the position vector. Now, acceleration, since this is a measure, what a time derivative tells you is the rate of change of something over time. Acceleration then measures how quickly the velocity is changing. And the velocity vector can change in 2 ways. So the velocity vector in 2D can change 2 ways. Its magnitude can change, or in other words, the speed can change. And or the direction can change. And so what I want you to notice is that is fundamentally different from what the acceleration represented in 1D. So that's different than 1D. In 1D, any acceleration meant the speed was changing. Because there's no such thing as turning in 1D. All you can do is speed up or slow down along the line you're on. Okay. In 2D, you can have acceleration even with a constant speed. Okay. So there aren't too many things that are fundamentally different as you go from 1D to 2D and 2D to 3D, but here's something that's fundamentally different. We picked up this idea of turning now, okay? So how do you visualize an acceleration in 2 dimensions? So first, sketch the object's path. Then draw the velocity vector tangent to the path. Third, draw the part of the acceleration that's parallel to the velocity. If the object is speeding up, this vector A parallel is in the same direction as the velocity. I don't know what's going on with my pen here. And if the object's slowing down, A parallel is in the opposite direction of the velocity vector. Okay, so you can think of the acceleration as being made up of 2 parts. One part that's parallel to the velocity and determines whether it's speeding up or slowing down. And then a second part that's perpendicular to the velocity that determines whether it's turning. Okay. If the speed is constant, then there's no part of this acceleration that's parallel. Okay. Now, fourth, draw the part of the acceleration vector that's perpendicular to the velocity vector. So this is the direction the object is turning. If the path is straight, then A perpendicular is 0. Okay. And then the total acceleration is just the sum of these two pieces. So there's the parallel part and the perpendicular part. This is the one that affects speed change. And this is the one that affects turning. Yeah, so right, this is the only one that exists in 1D because everything's parallel to everything if you're moving along a line. And then this is the new one that deals with moving off of that line. That's right. Anybody have any questions about that? I'll do an example to show you how this works. Okay, so let's say that the object's moving along this path from left to right. And let's say that we want to figure out the directions of the velocity and acceleration at that point. And we also have to know, and you can't tell from just looking at this picture, whether this is speeding up or slowing down. So let's say that it's slowing down. Okay. Again, if this was a position versus time graph of a one-dimensional motion, this gives you all the information you need to know whether it's speeding up, slowing down, because the velocity there is positive because the slope is positive. It's concave up, so it's speeding up at that point. But if this shows the path of an object in 2 dimensions, you need extra information to know whether it's speeding up or slowing down. One way that can be shown is if I mentioned that idea of taking snapshots. Say that you took a snapshot every 50th of a second or something, okay? What you would see isn't a continuous curve. You'd see a bunch of points, right? And depending on how close together those points are, it would tell you when it's speeding up and slowing down. If those points were getting closer together as time goes by, it's speeding up. If they're getting farther apart, no, it's opposite of that. If they're getting closer together, it's slowing down. And if they're getting farther apart, it's speeding up. Okay, so first let's draw the velocity vector. It's tangent to the path. So here's the velocity vector. And now we can start thinking about the acceleration. It's slowing down. So first we're going to draw the part of the acceleration that's parallel to velocity. Is it in the direction of velocity or opposite? Opposite. So there's a parallel. And now which way is it turning? There are 2 possibilities that are perpendicular to this line, that way or that way, sort of up or down.
Towards the inside of the curve.
Yeah, always towards the inside of the curve. That's a good way to think about it. You can also just think of, does this curve, which side of that line does that curve go to as time goes forward? But so in this case, so there's a perpendicular. And now what do we know about the total acceleration? Well, we know the directions of these 2, but we don't know the magnitudes. So we can't say exactly what the direction of the acceleration is, but we can say that if you add up a vector in this direction with a vector in this direction, you get something that's in between those 2 directions. So the total acceleration is going to be somewhere in this range of directions. Any questions about that?
Just a little earlier, in this example,
Yeah.
have we given that it's slowing down?
Yeah.
So, okay.
Yep. Okay, so let me do another example. So for this one, let's say that an object moves with constant speed. And let's say it's moving in a circular path. Let's say clockwise. And we want to know the velocity and the acceleration at that point. The velocity is tangent to the path. Is it speeding up or slowing down? Neither, it's constant. So there's no parallel part of the acceleration. Which way is it turning? This way or that way? That way. Toward the center, yep. And so we have a perpendicular part of the acceleration like this. Now the total acceleration is the sum of the parallel and perpendicular, but the parallel is 0. So this is the direction, and it is actually the total acceleration. So if you have an object that's moving with a constant speed, in this case it's a circle, the acceleration is always perpendicular to the path. If you have something moving with a constant speed in a circular path, the acceleration is always towards the center. Let's do the one we're missing so far, I guess. So let's say that this car is speeding up. And it's going this way. So the path of the center of mass of the car would be like that. Okay. Let's figure out the directions, the velocity and acceleration. So in this case, at this point, the velocity is tangent to the path with it, which for a straight line is just straight along the path. Okay. It's speeding up. So the parallel part of the acceleration is the same direction as the velocity. Is it turning? No. So there's no A perpendicular. And so the total acceleration is just that parallel part. Which, this, if you were doing this calculations connected to this, you just do it as a one-dimensional problem. Why not? It saves you a little work or whatever. But this is how the two-dimensional stuff reduces down to what we saw in one dimension for something that's moving along a line. Yep.
Why is turning? How would you draw it?
So if it was going okay, so the path is no, that's supposed to be the side. Okay. So it's traveling along this curved path. Okay. The velocity vector is tangent to that path at that instant. Okay. If it's speeding up, then the parallel part of the acceleration is the same direction as the velocity. This time it's turning. So the perpendicular part is like that. Okay. And the total acceleration then is the sum of those two, which means it's somewhere in this range of directions. Okay. Any other questions? Okay, let's stop there. So see you in lab tomorrow.